Hello everyone, my name is Nida Harman Nagli. Welcome back to my channel. This will be my sixth video of YouTube. So let's go with the very important topic of machine learning, which is VC dimension. So what is VC dimension basically? This the VC dimension is a core topic of machine learning. VC dimension is a measure of learning capacity or expressive power of a hypothesis space, a set of functions a model can choose from. It was introduced by Vladimir Vapnik and Alexey Chervonenkis, Foundation Future in Static Learning Theory. Let's proceed with my PPT and have the first slide, which is the introduction to VC dimension. A measure of a capacity complexity of a hypothesis class indicate the ability to shatter dataset include by Vapnik and Chervonenkis. VC dimension qualified how complex a model is based on how many different labeling patterns it can correctly classify. If a hypothesis class can correctly label every possible combination of labels for a dataset of a size D, we say it scattered that dataset. The largest such number D is the VC dimension. Let's go with my third slide, which is why is VC dimension important? It helps us to understand how well a model will generalize, perform on unseen data. A high VC dimension indicates a complex model that may offer fit, memorize data but fails to generalize. A low VC dimension may lead to underfitting. This model will be too simple. VC dimension helps us to balance this risk and choose suitable models. Understand model generalization, balance complexity and overfitting, and central to statistical learning theory. Let's proceed with the fourth slide, which is basic terminology explanation. Hypothesis classes. Set of function a model can learn. A set of all functions or models considered during learning. Scattering. H scattered a set if a classified all labeling. If a model can perfectly classify every possible labeling or a set of points, it's said to be a scattered that set. The third point, VC dimension, largest set that H can scatter. The maximum number of points a hypothesis class can scatter. It reflects the model capacity. Let's go with my fifth slide, which is VC dimension of a line in 2D. In 2D, a line linear classifier can scatter any 3 points, but it cannot always scatter 4 points regardless of configuration, especially if they form a convex shape. Hence, VC dimension is equals to 3 for linear classifier in 2D, where VC classified only 3 dimensions or 2 dimensions, 3 points or 2 dimensions diagram. Let's go with my another slide, the sixth slide. Formal definition. The VC dimension of a hypothesis class H is the cardinality of the largest set of points that H can scatter. The VC dimension of a hypothesis class H is defined as the maximum number of data points that can be scattered by H. It is a theoretical measure used to evaluate model complexity and learning limits. Let's go with my seventh slide, which is VC dimension in practice. VCH bonds generalization error. Larger VC, higher capacity, more overfitting. Smaller VC, means may underfitting. Let's go with larger VC. Larger VC implements the model can represent more complex pattern but risk overfitting. Another one, smaller VC, which is implies simpler model which may not capture the data well, leading to underfitting. In practice models with a moderate VC are preferred to balance bias and variance. Let's go with my 8th slide, which is VC dimension of common model. Here, I have been shown by using a table that how model and VC dimensions are replicated. Here, the linear classification in D dimension and VC D plus 1. If you can see the threshold function, which is the first in VC dimension. In model, the linear classification in D, here the VC dimension will be D plus 1. In model polynomial degree D, where D plus 1 is VC dimension. Model neural network, various with structure in VC dimension. Here, one more decision tree VC increases with the number of decision models. Let's go with my last slide. I hope you are clear with my slides, guys. VC dimension and overfitting. If VC is too low, the model cannot represent the data well underfitting. If VC is too high, the model might memorize the data overfitting. The ideal model should have a VC dimension that suits the size and complexity of the training data. Generalized bound. Here, the advantages of VC dimension. This inequality provides a theoretical bound on the true error where R functional edge of a hypothesis. Here the equation of VC dimension where R less than parenthesis S close parenthesis less than is the training error. Here H is the training error, VC is the VC dimension, N is the number of training samples, nu, which is the confidence level. This shows more data in N and a reasonable VC edge gives better guarantee on model performance. This formula has to be determined when the model have the best performance. Let's go with the summary of whole slide. Qualified model complexity. Here it helps in choosing model that avoid overfitting and underfitting. Balance under overfitting plays a critical role in model selections, theoretical learning guarantees, and generalization. Key in model generalization. I hope guys you are clear with my point. I hope everyone clear with VC dimension, the very important topic from machine learning. If you have any doubt, you can comment down to my YouTube channel. Definitely I'm going to answer you guys. Thank you for watching my video. Thank you for giving the attentive in my video. I hope you will like it. Thank you so much guys. Bye.